You know that sinking feeling when you accidentally mix the salt into the sugar bowl? Or maybe you just wish you could snap your fingers and get the pulp out of your orange juice? Well, life is just full of things getting mixed up, right? But in the world of chemistry, that's not really a problem. It's a puzzle. And today, we're going to find the solutions.
So here's the big question, really. How do you separate the inseparable? I mean, when things are blended together so perfectly that they look like one single thing, how on earth do you pull them apart again? It can seem totally impossible, but believe it or not, it's a challenge chemists tackle every single day.
Okay, so the secret isn't magic, even though it kind of feels like it. It's really all about knowing which key fits which lock. See, for every single jumbled up mixture out there, there's a specific technique designed to unmix it. And in this explainer, we're going to build your master key ring.
All right, so before we can start separating anything, we need to get familiar with our tools. And that means two things: the actual physical equipment you'd see in a lab, and, just as important, the language we use to describe what's actually happening.
So check these out. These are the classic tools of the trade. Yeah, you've got your beakers and flasks for holding stuff, but the real heroes of separation, they're items like the filter funnel, which is basically a fancy sieve, and this really cool piece of glassware called a condenser. And trust me, we'll be seeing that one in action very, very soon.
Okay, so this gives us the vocabulary we need to talk about mixtures. Let's just take seawater, for example. The water, that's the solvent. It's the liquid that's doing the dissolving. The salt is the solute. That's the stuff being dissolved. And when you put them together, they form a solution. See? Simple, right?
Now this is the very first clue every chemist looks for. Before you even think about grabbing a tool, you have to stop and ask, what am I actually dealing with here? Is it a solid mixed with a liquid? Is it two liquids all mixed up? This chart is basically our roadmap. The second we know what kind of mixture it is, we know exactly which path to take.
All right, let's dive into our first challenge: a solid mixed into a liquid. This is probably one of the most common puzzles you'll ever find, from something as simple as muddy water to your morning cup of tea.
And right away, our path splits into two. The big question is the solid insoluble, like sand in water, where you can still see all the little grains floating around, or is it soluble, like salt in water, where the solid just seems to, poof, vanish completely? The answer to that one question determines everything we do next.
Okay, so for those insoluble solids, we use our very first technique, filtration, and it's just beautifully simple. You literally just pour the mixture through a piece of filter paper. The liquid, which we call the filtrate, passes right through. Meanwhile, the solid, which we call the residue, gets trapped. It is exactly like making coffee.
But wait a second. A coffee filter isn't going to help you with salt water, is it? The salt is dissolved. It would just flow right through with the water. So now we've got a much trickier puzzle on our hands. How do you get pure, drinkable water from the salty ocean?
The answer is something called simple distillation, and it all works by taking advantage of different boiling points. So we heat the seawater. Water has a much lower boiling point than salt, so it turns into steam, leaving all that solid salt behind. That steam then travels into our friend, the condenser, which is cold. It cools the steam down, turning it back into pure liquid water that just drips into a clean flask. And boom, mission accomplished.
But what if you don't care about the water? What if you want the solid back? Well, for that, we use a different technique called crystallization. First, you gently heat the solution, just enough to evaporate some of the water and make it more concentrated. Then, and this is the key, you let it cool down nice and slow. As it cools, the water can't hold all that salt anymore, and it starts to form these beautiful, pure crystals that you can just filter out. All right, time to level up the difficulty. What happens when you mix two liquids together, like say ethanol and water? I mean, they can mix so perfectly you'd never ever know there were two different things in there. So how do you unscramble that? So this setup here might look a little familiar, but there's one really crucial upgrade. On the left, that's the simple distillation kit we just saw. But on the right, for separating two liquids, we've added that tall, vertical piece of glass. That's a fractionating column, and believe me, that column changes everything. The secret here, once again, is boiling points, because different liquids boil at different temperatures. So when you heat the mixture, the liquid with the lower boiling point, in this case the ethanol, starts to evaporate first. It rises up that fractionating column, which is full of glass beads. And as it rises, it keeps condensing on the beads and re-evaporating, getting purer and purer with each step. Eventually, only the pure ethanol vapor makes it all the way to the top to be collected.
All right,
For our final challenge, let's have a little bit of fun. We're going to try and separate all the hidden colors inside a single drop of black ink. Now you can forget everything we've learned so far, because this technique is totally different. We're going to have a race.
This is called paper chromatography, and it's all about solubility. So here's how it works. We put a little dot of ink on a starting line. Then we dip the edge of the paper into a solvent. As that solvent starts to creep up the paper, it carries the different colored dyes from the ink with it. And here's the really clever part. The dyes that are more soluble in the solvent are the fastest runners. They travel farther up the paper. The less soluble ones lag behind. And just like that, the colors separate out.
And get this, we can even score the race scientifically using something called the retention factor, or RF value. It's really just a simple ratio. The distance the colored spot moved divided by the distance the solvent moved. What's amazing is that every chemical has its own unique RF value under the same conditions. That makes it a super powerful tool for identifying unknown substances. It's basically a chemical fingerprint.
And so that brings us right back here to our master key. We've seen it all in action now, haven't we? A chemist's first job always is to figure out what kind of mixture they have. Is it a solid and a liquid? Is it two liquids? Once you know that, you know exactly which tool to grab from the toolkit, whether that's filtration, distillation, or chromatography.
And look, these are not just neat lab tricks. This is real-world stuff. Fractional distillation? That's how we get gasoline from crude oil. Distillation is a huge part of how we get clean drinking water. And chromatography? It's used everywhere from forensics labs to food testing. These simple ideas have a truly massive impact. So the next time you look around, just ask yourself, what hidden mixtures are all around me and what key would I use to unlock them?